We're going to talk now finally more about continuity. So we have said that conversationally, a continuous function has a graph that is connected. That is, we can draw the graph without lifting our pencil from the paper. And that's a nice way of thinking of it. So we're not going to change that kind of intuitive understanding of what continuity is, but we're going to add some more formality to it in terms of a definition. And we're going to talk about what does it mean mathematically to be continuous at a point, on an open interval, and on a closed interval. And to start with, sometimes I think we get a better understanding of where a function is continuous if we understand where it is not continuous. So we're going to say there are 4 ways. Oh, come on, pen, cooperate. I think I have a slick spot on my iPad here. Let me try this a little again. We have 4 ways. That's supposed to say, there we go, ways a function can, struggling to write here, can fail to be continuous at a point. It's not writing very well. Okay, I think that's fairly legible. So here are the first 2 ways. So we can have a function that has a hole in the graph. So at this point right here, it is not going to be continuous because you can see you would have to lift your pencil from the paper. You could also have a hole in a graph that was defined to be something other than what would fill in the hole. Each of these 2, these are our first 2, these are have a name. They are called removable discontinuities. Those are removable discontinuities, and they are considered removable discontinuities. Having trouble writing still. These are removable because you could fix them. You could fix that place where it's not continuous by just redefining the function at one point. So if we just redefine the function at that point, then we could make it be continuous. Likewise, if we would redefine the point here and move that point down, it would fix the discontinuity. And so that's what we mean by a removable discontinuity. Another kind can be something that looks like this, where we have that left-hand limit different than the right-hand limit. That is known as a jump discontinuity. And the third kind is where we have, struggling to get this to write. It's supposed to be my asymptote, which isn't showing up. Something that looks like this, or they could go in different infinities. Either way, anytime you have a vertical asymptote, that's going to be known as an infinite discontinuity. Really struggling here. So those are the 4 ways: a removable discontinuity, a jump discontinuity, and an infinite discontinuity. Okay, I'm going to go to a new screen and we'll talk about our formal definition there. So let's talk about continuity at a point. So continuity at a this is the big one here. So a function f is continuous at x equals c if the following three conditions are met. 1, the limit as x approaches c of f of x has to exist. Secondly, the function f of c has to be defined at c, so f of c exists, so the function must be defined there. And thirdly, the limit as x approaches c must equal that value of the function. Okay, and sometimes people will say the shortened version is just this third one. That is, they'll say the limit exists, the function is continuous if the limit is equal to the value of the function. That means that we're assuming then that the limit exists and the value of the function exists. So let's talk about further about continuity on an open interval. So continuity on an open interval. So f is said to be continuous on the open interval from a to b, and we show the open interval with the parentheses because we're not including a or b. That's what makes it open. If f is continuous at each point in the interval. So not too earth-shattering. Hopefully that makes sense. So for example, if we said that f of x is equal to, say, x squared, then that's continuous for all real numbers. So we would say it is continuous from negative infinity to infinity. And since you can't include the endpoints, that's considered an open interval. If you said g of x was 1 over x, then you could say that is continuous on the open interval from negative infinity to 0. Remember, it's got a vertical asymptote at 0, so it's not going to be continuous there. And it's also continuous on the interval from 0 to infinity. Say something like h of x is natural log of x. If you remember, you see the graph of log x is there. That's going to be continuous on the interval from 0 to infinity. Okay, new screen, and a little bit more challenging is this idea of continuity on a closed interval. So let's talk about this a little bit. So continuity on a closed interval. So if you remember our definition of continuity, so at a point has these three conditions. The limit must exist, and the function must exist at that point, and the limit must equal the value of the function. So the problem with a closed interval that we're going to work around is, suppose you think of something like, say, f of x equals the square root of 9 minus x squared. So what that looks like is a semicircle that has radius 3. Now we would like to say correctly that this is continuous on the closed interval from negative 3 to 3. The problem with our definition as it stands is for the limit to exist, it has to be a two-sided limit, and we have that problem at the endpoints because you can't say the limit exists at negative 3 because the function doesn't even exist there. So the way we fix that is just by changing how we define the limit on a closed interval. So we say that if the function is first of all continuous on the open interval. The function is continuous on the interior, so on the interval from A to B, open interval. And then we talk about continuity at the endpoints by saying if the limit as x approaches that left endpoint A from the right, so we don't worry about trying to come in from the left, if that limit is equal to f of A, and then we do that at the right endpoint by saying if the limit as x approaches B from the left is equal to f of B, then f is continuous on the closed interval from A to B. Okay, so here is an example of a function that is continuous on a closed interval. And another example of one that's closed at an endpoint anyway, if we said, say, g of x is equal to the square root of x, we know what we like to say is that that's closed on the intervals called half open or half closed from 0 to infinity, and that is true. So it is going to be continuous at that endpoint on the left, and then it's continuous forever to the right. Okay, so I'm going to stop here and make a second video for the next part.